So the topic of today's presentation will be on QA/QC of deep foundation testing. There are many people joining from different parts of the country, as well as some of them from overseas. Can you all type out from which region you are all connecting from? Please type out which region you are connecting from, so that Zubair Ali from Pakistan is joining. Others, which region you are connecting from? Could you please type out? I know you are clearly hearing me, so I'll start the presentation. Indonesia, people from Indonesia. How about the others? From Nepal, from India. Yeah, Dubai. Thank you. So all of you can hear me loud and clear. So the topic of today's presentation is QA/QC on deep foundation testing. We sent out some questionnaire. Many of you have asked several questions. Probably I will try to address during the course of presentation, perhaps all the questions that we have received from all of you. So at first, why do we use deep foundation? In order to transfer the loads from the superstructure when you do not have a competent soil to adopt shallow foundations, then you use deep foundation. During the construction of deep foundation, there are several anomalies that we witness. Okay, the pile top can be damaged. There is a severe necking in the pile, the bleeding in the pile. The pile toe could be damaged if it's a driven pile, severe defect. Even steel piles have the same problem. If the stresses are not controlled during driving, the piles could be broken somewhere along the shaft. The toe damage for a steel pile driven to rock. And you can have serious defects in any of the pile elements, even for the drill shafts. So once these drill shafts are installed below the ground, you will no way be able to identify these anomalies unless we resort to some kind of testing. So the success of a geotechnical engineer, particularly a foundation engineer, is buried in the ground. When you go to any monumental structures like Burj Khalifa or Eiffel Tower, so we all take selfie from the ground, and behind us we have those monumental structures. We post it on our social media pages, but whenever you have a good success of foundations, you can't do that well because it's buried in the ground. But if we do not make any assessment of these anomalies, is it safe in terms of load carrying capacity and serviceability criteria? So one need to address. So we represent Pile Dynamics, who are pioneer in the deep foundation testing for the last 5 decades. We represent them in this part of the world to provide training and tech support. So this also makes us more responsible now in the industry, and also professional responsibility to disseminate knowledge, and that's where we are here. So there are several deep foundation testing methods that are available. So prior to pouring the concrete, you have squid and the shape. I'll explain to you what is squid and what is shape. After pouring the concrete, you have different integrity assessment methods: the pile integrity test, the cross-hole integrity test, and the thermal integrity profiling. So I'll touch base each of these methods and show you some results. I'll also touch base on bidirectional load test. There were some questions also on that for conducting the static load test. And finally, before I conclude, so let me share with you some case studies which we have been involved in the forensic study in evaluating the integrity and load carrying capacity of deep foundation in several of our projects, and what is the way forward. Okay, so SQUID is a shaft quantitative inspection device. Okay, so this estimates the thickness of contamination in the pile borehole, particularly useful for rock-socketed pile, which is deriving its capacity from the base. We do not want any polymer or bentonite to be accumulated at the pile base. If the thickness is more than the recommended thickness from some of the guidelines, the load carrying during the load carrying capacity, the pile will experience large settlements, and thus it will not carry the requisite load. And therefore, it is important to quantitatively estimate what is the thickness of contamination so that one could resort to some cleaning process before pouring the concrete. So the squid is a tool like this can be connected to the Kelly bar of the piling rig directly. It has 3 penetrometers at the base. It could be a pointed tip or a flat base with 10 centimeter square area. And there is a retractable plates. So when you apply a force from the Kelly bar, the cones will penetrate into this contaminated layer. The colored zone is a contaminated layer, and you get a force and also the displacement because the retractable plates move up and you can measure the force displacement. The philosophy of this method is using a Terzaghis consoled bearing capacity theory, where the contamination is treated as a cohesive material. If the shear strength is around 12 kilopascal or less, it is expected to displace during concrete. If it is more than 100 kilopascal, it's treated as natural material. So and that's how we arrive at the debris threshold value of 0.09 kilonewton for a 10 centimeter square area and 0.7 kilonewton for a 10 centimeter square area for 100 kilopascal shear strength. So the displacement difference between these two thresholds is the thickness of contamination at that cone level. So we have 3 cones. So you have the average of these cones should be around less than half an inch. So if it is more than half an inch, probably you resorted to some kind of cleaning. So airlifting, bucketing, or whatever the means that you have in the project site, and ensure that this thickness is less and you can proceed with the concrete. So we commissioned this in one of the metro projects in Bangalore during COVID time, and you see the measured thickness of contaminations is nearly 4 inches. Okay, but the contractor did not clean this because this was a pilot project. Then later on, he informed, yes, he did clean and put the concrete. But later on, subsequently, we commissioned this another project for the same project. If you could see here, the mark is the contamination is sticking to the cones and the displacement. So it really confirms that the thickness of contamination is really big. So another project, same thing happened, but there were several cleaning process, about 4 to 5 times. And later on, when you finally tested, the thickness of contamination was less than half an inch, which is prescribed in some of the federal highway guidelines in the US, and the same thing could be adopted here. And then the reinforcement was lowered down and poured the concrete. So this squid will estimate quantitatively the thickness of contamination at the base of the pile borehole in order to not experience large settlements during the static load test. Now coming to shape, again is another quality control tool prior to pouring the concrete, which is called shaft area profile evaluator. So this shaft area profile evaluator, like squid, also could be connected directly to the Kelly bar of the piling rig, or it could be lowered from a winch. It doesn't require any force, but the squid requires a force. So this shape has 8 ultrasonic sensors embedded radially. When you apply the voltage, the piezoelectric element changes its geometry and releases the pressure waves. Okay, and it hits the pile boundary wall. So there are 2 sensors inside, which is embedded at a known distance, and it calibrates the wave speed. So 1 scan per second. As you lower the tool, you'll be able to identify the geometry of the pile borehole excavation. You need a wet borehole to perform this shape, but PDI has also developed a LiDAR-based sensor technology for a dry hole. But the same unit can't be used for a wet and a dry hole. You need to have 2 different units. Probably in the next upgradation, maybe next year, they may come out with a single tool for both dry and a wet hole. So we also commissioned this in several of the infrastructure projects, metros, and some port projects. So what you see around the periphery, you have the radial sensors at different cross sections. You can get the shape of the pile borehole, and more importantly, the eccentricity of the borehole itself. So you see the offset divided by the length of the pile is your eccentricity. Normally, the eccentricity of about 1.5 to 2% is permitted in many of our infrastructure projects. And if this offset is more than the prescribed limits, probably moment is induced, which will reduce the load carrying capacity of the pile. So this is a powerful tool to get you the shape of the pile borehole excavation, the eccentricity, and the volume of this excavation as well. So this is similar to the cordant technology, which is normally used as well to get you the shape of the pile borehole and the eccentricity. And this is very common in many of the Middle East projects, and shape has been in the market for several years now and been very popular in US and Europe, and also we try to commission this in India too. So two quality control methods, shape and squid, prior to pouring the concrete. Now after pouring the concrete, we are always interested to do a static load test by Kentledge method, by reaction method, and now you have the embedded jack technology, the bidirectional load test using your Osterbeck cell, the super cell, the O cell, or so on. So this is a YJack, is a Malaysian company who has patented this technology, and we partner with them to perform this bidirectional load test. I'll talk about this high strain dynamic test in a bit. So when you put the Kentledge, safety issues are concerned. So you can see one of the project site in Singapore, the Kentledge. I'm sure there are many other cases as well, which is a safety concerns. So the bidirectional load cell load test can eliminate some of these safety concerns. So this test consists of embedding a jack into the pile before pouring the concrete. So the level of this jack we call this as the balancing level. You need a thorough geotechnical investigations to balance the reaction from the shaft at the top of the jack, and also the reaction from the shaft and the end bearing below the jack. So if you do not have a accurate geotechnical investigations, probably these balancing levels could go a little off. So during testings, you have the two-way loading, so pushing the top wash up and the bottom down. And what you get from the maintained load test or the top loadings, you get this load settlement curve. From the bidirectional load cell, you get the butterfly curve, pushing the top portion of the pile and the bottom. And you have some analysis procedures to convert this butterfly curve into an equivalent top load pile displacement curve. Okay, so this has also been very popular in the industry. When you could see the difference between the static and the YJack methods, safety issues and the time constraints, and also the economics, particularly when you're testing large loads. So this bidirectionals becomes very economical. Now you could embed this jack to the reinforcement. If you are splicing the reinforcement, you can do that and pour the concrete when it is ready, and then with the telltales you measure the displacement and apply the force. There are many projects YJack has performed in Southeast Asia, and we wanted to commission that in Indian market as well. And recently we were successful in a couple of projects. One is for this Versova Bandra Sea project, and you see these jacks have been embedded in the reinforcement. The splicing is done, concreting is done, and you have these telltales and the arrangements, and it is successfully completed. This was a project in Kochi, as okay. So two projects we have successfully completed in India, and I'm sure there will be many more projects in the upcoming days. So we talked about the shape, we talked about the squid, we talked about the bidirectional load test. Now, After pouring the concrete, we also want to ensure that integrity of the deep foundation elements are assured. Okay. So there are many methods. The rudimentary conventional for very long time is the low strain pile integrity test. And you have the cross-hole sonic logging test, probably about nearly 2 decades. Now, the recent methods, emerging method is the thermal integrity profile. So I'll touch base on all the 3 methods now. So the low strain integrity test is a quick and cost-effective method to evaluate the shaft integrity of concrete piles. And this test is able to provide us the information on pile continuity, location of defect, and the degree of defect. These integrity methods, in fact, none of these integrity methods will give any idea about the load carrying capacity. So this method PIT is performed with a handheld hammer, a sensitive accelerometer, and the pile integrity tester. So on the top of pile, you mount an accelerometer with a small handheld hammer. You give an impact, and you will record this velocity time history. This is the top of the pile, and you see the toe of the pile. So the response from the toe. So you need to prepare the pile top by removing the contaminated concrete and go to the sound concrete. Okay, and mount an accelerometers. After preparing the surface, give an impact with a small handled hammer and record the response, the velocity time history with an pile integrity tester. For an idealized pile, it has a good shaft. You see the top of the pile, and this velocity traces the x-axis to get the toe response. If there is any defect in the pile with a reduced impedance, you see an early positive response in the velocity trace, okay, which indicates a severe defect in the pile. Okay. Now, it's also important that you calibrate the hammers, because one size doesn't fit all. So we have piles from 300 millimeter diameters to 3 meter, maybe even more monopiles. The length of pile could be just a short stub pile of about 1.52 meters to as deep as 70-80 meter in the country is not uncommon. So therefore, you need to calibrate different hammers and use just hammer that gives you consistent results and also the toe response. And use smaller hammers, particularly to evaluate defect close to the pile top, because if you use a heavier hammer, the defects close to the pile top will get masked, and you get a very wide input pulse width, okay, and you will not see any defect close to the pile top. So this is an example of a typical PIT results using a 10 Newton hammer. You see clearly the top of the pile and a pile toe response. So pile top preparations is the key to get good data. So without good data, no matter how sophisticated your softwares and the instruments, it's irrelevant. And if you do not have good pile top preparations and you see a noisy data, so this data cannot be analyzed, and you tend to probably under high duress to manipulate the results or give some results which may not help any of the stakeholders. So good testing is very important. So some data sets were testing under a tower. You see the velocity time history, a huge positive response just before the toe response, indicating serious defects in the foundation element. When they actually cored this pile, you could see the severe defect in the concrete, which corroborates the results from this PIT test. Okay. So whenever you see a positive response, positive negative cycle, and this is treated as a defect. When you see a negative positive cycle is treated as a bulge. So bulge is not a concern for the load carrying capacity of the pile. Okay, so now the top pile 27. This is an idealized, very good pile. You don't see any positive response. So it's a good pile. And the second one, you have a negative positive cycle. So the negative response indicates a bulge in the pile. And the third one, 28, has a positive response close to the pile top, indicates serious defects close to the pile top. Okay, and this is severe defects near the pile top. So it's very straightforward unless you get a good data. So if you do not get good data, then interpretations becomes extremely complex. So this PIT will help us to locate major defects. It's limited to general interpretations rather than exact details to demonstrate safety of any pile foundation. Qualification of pile for integrity is essential. So let us not use any of our heroic efforts to read more than what the data really tells us. Okay. So what is the limitations of this pile integrity test? The wave speed of concrete varies between 3,300 to 4,300 meters per second. So therefore, locating the toe with this wide variation of the wave speed could be in an error between 5 to 7%. So one of you have asked me a question. So how do we check a 35-meter pile subcast to the correct depth? Okay, if you calibrate the wave speed properly for the concrete that is being used, if you perform a pile integrity test, then you will see that toe respond exactly at 35 meters plus or minus about 5%. Okay. Now I quickly jump into the dynamic load test, because both the low strain integrity test and the high strain dynamic load test has same theoretical background, that is based on your one-dimensional wave propagation theory. Okay. So conducting a dynamic load test consists of instrumenting the pile top with strain gauge and axiometer. The strain gauge measures the strain during under an impact. You know the modulus of the material, which is concrete or steel, and then you know the cross-sectional area, you can get the force. The axiometer will measure the motion of the pile. Integrating the acceleration will give you the velocity. So force and velocity are proportional with a constant impedance. I'm not going to derive this. This is a part of the training, but I just give you why you are using the strain and the axiometer. So when you mount a pair of strain gauge and axiometers just below the pile top, usually around 1.5 to 2 times the diameter of the pile below the pile top, with a cushion at the top and a dead weight you drop on the top of pile, you will acquire a force, velocity, time history. So you need to see that force and velocity to be on top of each other to ensure that both of them are proportional. And as you see the separation of force and velocity along the length of the shaft, this is the top of pile like your PIT, this is your toe, and you see a toe response. The separation of force and velocity indicates your shaft resistance. So if there is no separation between force and velocity, if they both of them are exactly on top of each other, you do not see any shaft resistance. Now, how much dead weight to be dropped on pile? It's usually between 1 to 2% of the ultimate capacity to be proved. So 1% for friction pile, end bearing pile or a rock socketed pile, and 2% for a friction pile. Now, when you get this data set, force, velocity, time, history, you bring this data set into the CAPAP software. So the CAPAP is a signal matching techniques to compute what is your system, because you know the load from the measurement of strain and the force, and you know the movement from axiometers. But what we do not know is the system, the distribution of the resistance between skin and the end bearing, and also the other dynamic parameters. So iteratively, you run the analysis to ensure that your computed and the measured signatures are exactly on top of each other. So then you have arrived at a solution. So go to the output, you get your total capacity, skin friction, and end bearing. So for both this pile integrity test and the high strength dynamic test, you need to understand one-dimensional wave propagation theory. It's common for both. Proper practice, how to do the test right at the first place, what are the precautions to be taken, how to instrument the pile, how to get the data, how to make an assessment of quality of the data, the application and the interpretation of data sets. And finally, for the high strength dynamic test, we have to analyze and understand about the case pile wave analysis program. These are part of the training we conduct. So Sangeetha will give you more details towards the end of this presentation. So now we discussed about the squid, we discussed about the shape, which is prior to pouring the concrete. Then we discussed about the bidirectional load test, a glimpse of high strength dynamic test, the instrumenting strain and axiometers below the pile top and getting a force velocity time history, bringing the data set into the CAPWAP to perform a CAPWAP analysis to get the total capacity and the distribution of capacity between skin and the base. Now let us examine other two integrity methods. One is the cross-hole sonic logging test. So one of the limitations of the pile integrity test or the pit testing is if you encounter any major defect and any other defect below the first major defect, the pit cannot identify, because what you see, the response will be a secondary response from the first major defect and not exactly the defect itself. So that limitations could be overcome from the cross-hole sonic logging test. And we need to have an evaluation of the integrity for every drill shaft, because these are few in numbers, particularly for our infrastructure projects. For example, your metro rails or high-speed rails, there are 4 or 5 piles per group for a pier. So each of them should be integral, okay, or homogeneous. So this cross-hole sonic logging test requires embedding the access tubes, which is around 3 inches in diameter steel or PVC tubes to be embedded along the reinforcement cage. And you have to take it to the bottom of the pile. Take it to the bottom of the pile. Okay, how many tubes are required? Generally, about 30 centimeter diameter one tube is necessary. So a 1.2 meter diameter requires 4 access tubes embedded to the reinforcement. And then you insert the probes, the sonic probes. One is the transmitter, the other one is the receiver. So you can have one diagonal being scanned, the other diagonal can be scanned. So you have 2 major diagonals and 4 perimeters. So as you lower the probes to the bottom, one is the transmitter, the other one is the receiver. The sonic waves is emitted from one tube, is received from the other one. And as you pull the probes up, bottom up, at every 50 millimeter, it scans the time the sonic waves takes to travel from the transmitter to the receiver. If the concrete is homogeneous, I think the time is same, the wave speed is same, the velocity is same. So if you have a major defect at any location, then you see a delayed time of arrival. So that indicates there's some anomaly in the shaft. Okay. Now, these days, the latest model has the sonic probes as trans receivers. So it can transmit as well as receive from the other probes. So all 4 trans receivers could be put into the tube simultaneously, and one pull scan all these possible 6 combinations. So the efficiency has improved by 6 times. This is the ChampQ latest model to have these color codes, and also these are the trans receivers. Okay. So we also commissioned this in some of our projects to find the integrity. So these are the trans receivers which are color coded with the cables as well. And now the test setup to conduct this cross-hole sonic logging test with the access tubes embedded to the pile. So once you embed this pile, immediately after pouring the concrete, the access tube shall be closed at the bottom, and you fill this water because we do not want the debonding of these pipes. So, and also you need a medium for the sonic waves to pass through. So that's why you fill it with water. Okay. And this is the reinforcement cage setup. So tie these access tubes along the reinforcement cage. And you prepare the test setup. This is a depth encoder, okay, which actually measures the depth as you pull the cables. The boys are ready to pull these probes, which is already into the access tube. Okay, and then you do the data test setup and the input data, the distance between the probes you measure and input, the length of the access tube and the diameter of the pile. So it computes your circular cage diameter as well as the distance between the access tubes to get your velocity profile or the wave speed profile. So then, as in one pull, all 6 possible combination could be recorded. And this is a waterfall diagram. I'll explain to you in a bit what is this waterfall diagram. So from the sonic test, the emitted signals has an amplitude, and so with your received signals with a reduced amplitude. So this received signals is after a transit time. So if this transit time is uniform along the shaft as you pull up, then your concrete quality is homogeneous. So from these received signals, you have a positive, negative, positive, negative, positive, negative. So if you nest it, the positive as black, and this is white, this is black, this is white. So black, white, black, white, black, white. This is nested to a waterfall diagram. As you pull the probes up, this is a waterfall diagram. And I could see there some locations there's a complete loss of signal, indicates there is a serious defect. This is one of the force defect at that location, perhaps around 5 meters. Okay, there you see a complete loss of signal. So the interpretation becomes really straightforward when you have this traditional waterfall diagram. And you see the signal strength is very good. And the first arrival times, this is a delayed time. So the first arrival time is wherever it's delayed, it indicates a serious defect. That also is reflected from the leading edge of the waterfall diagram. If you actually write down like this, okay, then there's a peak, then there's a peak here, then there's a peak here, and also a peak here. Okay, sorry about my shabbiness in the drawing. There is a peak here. So this first arrival time should actually match with your loss of signals in your waterfall diagram. So this is your first arrival time, leading edge, and this is your first. So if both of them are similar, in this case it is, you actually have good data set and you can interpret from that data. So how do you find defects? The defects is very good when you have a good signals, and the pile is defective if you have a reduced signal strength, which is an integral of the signal strength over a time. It gives you an energy, and also the delayed in the first arrival time. So the defect is identified if you have a reduced signal strength or lower energy. In this case, it has a very low energy compared to a good shaft, or a delayed arrival time. In this case, it's a delayed arrival time, or both. Okay. So after you do the test at wherever the locations, so unlike PIT, in this CSL, you can identify defects at multiple locations along the shaft. So once you get the results, there is a first arrival time and energy reduction. So here are some guidelines to qualify the pile. If it is less than 10% to of the first arrival time, less than 6 decibels is good, minor defect, poor or flaw. But recently, after 2019, there were several researchers and the industry experts come together to arrive at a DFI guidelines to qualify the piles based on the CSL, based on the first arrival time and the relative energy reduction. If the data points fall in the green, it is absolutely acceptable. In the red zone, it is highly abnormal, so requires some remediation. In the transition zone, in zone B, if it's closer to the green, you give benefit to the pile. If it's closer to the red, probably you may have to relook into the remedial measures. Okay. So let me show you some data set. So in this waterfall diagram, it's straightforward. It's complete loss of signal at the pile toe. When they actually exhume the pile, you could see severe defect in the pile. Okay. So as we commission in one of our accreditation project site, and you see perfect waterfall diagrams, so there's no problem in this, and this is qualified to be a good pile. And in the same region, is a forced defect. You could see a severe defect with indicating complete loss of signal in the waterfall diagram. So it identified as pile with defects. Okay. Let us see some more data sets. So this is a good pile, has no loss of signal in the waterfall diagram. Okay. This is also good pile, no problems. But when you see this data set at similar depth in all possible combination at around 25 to 28 meters, you see there is a loss of signals, which indicates a severe defect when this pile was cored at the center of the pile. And you could also corroborate this with the poor quality concrete that was recovered from the pile. Okay. So one of the limitation of the CSL is since you are measuring only within the reinforcement, you are able to only look at the integrity of the shaft within the reinforcement. It doesn't give any indication or information about the quality of the concrete outside the reinforcement or the alignment of the cage itself. Okay. So now let us examine some more data sets. So can you type out on the chat box what you think on this pile based on your waterfall diagram? Please type out on the chat box. Can you type out on the chat box? Is it a good pile or a bad pile? Hello, everybody. You need to interact with me. Yes, good pile, good pile, good pile, good pile. Thank you. Thank you, all of you. I hope you are attentive now. So the same is indicated by PIT as well. You see the top of pile and a toe response, and you do not see any positive response along the axis. So it is qualified to be a good pile. Okay. So how about this? Please type out in chat box again for me. Thank you all for participating. Please type out in the chat box what do you think on this pile. Is it a good pile? Habib says good pile. Tara said good pile. Arun Pandit said good pile. Thank you. It is a good pile. Okay. Now, let me go to another one. So what do you think on this pile? Please type out on the chat box now. Continue doing the good work. Toe damage, Arun says good pile. So it's a defective pile. Just nice, a defective pile. Soft toe is there, soft toe is there, toe problem, toe problems. You are able to see a loss of signal at the toe. It indicates a toe defect, and also you see a positive response in the PIT near the toe. You could as well adjust this because you know the wave speed will vary, but already your wave speed is 4,300. You can't increase this for a concrete pile, maybe 5,000. Then you may avoid this toe defect interpretation. But since the CSL corroborates very well, and also you have exceeded the maximum wave speed, you can't change your wave speed. Therefore, this is qualified as toe defect, okay, or a doubtful pile, possible damage towards the toe. Fantastic, guys. Thank you for at paying attention. This one, please type out again in the chat box. What do you think? People says toe defect, toe defect, toe damage, somewhere towards the bottom of the pile. You see a defect there towards the bottom of the shaft. Okay, and this is also qualified to be doubtful pile. Okay, so you have a good correlations between the PIT and CSL. So I can show you hundreds of case studies, but paucity of time, so I think we can stop here. So when you see a anomaly in all the combination of the CSL scanning, that means your defect is throughout the cross section, at least within the cage. It's a short pile, maybe a free end at that level, so you do not need to do anything. If it's a intact or homogeneous pile, you did not do anything, right? But if you have a defect visible in some combination, but absent in other combination, that means the defect could be localized to certain quadrant. So therefore, you can have a tomography analysis to be performed to identify which quadrant and the degree of defects that exist in the pile. So you can actually plan your remediation measures. For example, here, this is in this quadrant. So you may able to drill a hole to that level and then grout it. Okay. So if there is a defect in all the combination, you don't need to do anything. If there is a defect, no defect, you don't need to do anything. If there is a visible defect in some combination and absent in the remaining combinations, you can resort to a tomography testing. Now, to sum up on the CSL, it's an automated defect analysis can assess the quality of the concrete, provides numerical and graphical presentation. Shaft with no defects or full section defect require replacement or repair need no extra analysis. Shaft with local defects can be analyzed by 3D tomography. Now, the limitation of CSL, you are scanning only within the reinforcement. Okay, you're not having any information outside the reinforcement. And also the alignment or tilt of the cage is not known. So how to overcome this limitation of CSL? So we have what we call as thermal integrity profile. Okay. So let me pause a minute here and then want to have your feedback on that. Do you have any questions so far? Please type out in the chat box if you have any questions or you do not understand anything. So let me just summarize before you start typing. Please start typing of your questions. We talked about the squid, we talked about the shape, we talked about bidirectional test using YJAC technology. We talked about the pile integrity test. We talked about the high strength dynamic test and the cross-hole sonic logging test. Please type out for me if you have any questions so far before I. Squid, what is the smallest diameter in which it can be used? Squid, you require a minimum of about 700 millimeter diameter. And so with the shape, what if the tube block is CHL testing? So you can't get that. So you identify either is a defect, but it's not a defect. So you may have to be a little extra cautious in qualifying. So Bharat is telling. So what's the percentage of P? What is the smallest diameter? I answered that. Shape should bit be used in clean the boreholes or even with bentonite. Cleaning process, you can use any cleaning process that is there. So usually they use a bucket for cleaning, airlifting, or jetting actions. So whatever they mean, the borehole has to be clean. Okay. So how to identify if the data was taken without poor pile head preparation? I already showed you if you have several noise in the data and you do not see any toe response, it's very difficult to analyze the data. If the pile is defect towards the top below the soil, how to identify? So let me show you after I present it. What percentage of pile CSL test should be conducted? So this is very subjective. So what is recommended is you use a consumable CSL tubes to embed that can built into your cost. But wherever you have a doubt, you can go and test it. Okay. If you do not put that pipe during concretings, you can never do the testing. Okay. So some projects, very important projects, 100% of the pile is tested both with PIT and CSL. But for other projects, you may have to embed the tubes, but you can resort to do that testing wherever you have the doubt. PIT, since it is very simple, very economical, 100% of the pile is tested. And if you have doubt in PIT, you can go and do CSL test. Okay. PIT works with help of stress waves, but both have wave speed in similar ranges. CSL and PIT, it will be not exactly the same because these waves are different. You may have slightly different wave speed from both these methods. Okay, but the abnormal ones could be easily identified. from these methods. And one of the main objective of PIT is to identify major defects. Okay. Now the CSL has another problem. So the access tube has to be vertical. So if you have a inclined access tube, then your wave speeds are shabby all over the place. So the SPBs may not be a measure in CSL, but identifying the defect could be a measure in CSL. So the tubes are blocked. I already answered. If the tube is blocked, maybe I will pull out some data set to show you this. You can't get the data if the tubes are blocked, because if tube 1 is blocked, then 1, 2, 1, 3. So all the 3 data sets, you do not have the data. If dirty water affect the quality of results, may not be, but you have to ensure that you do not have any impurities in the tube, which will impede the passing of the probes. That's very, very important. And perhaps you should do the test probably within 7 days, because the longer time you leave, there will be a debonding in the pipes. The debonding will also not give you a good results. You tend to interpret the pile to be defective, but it may be due to debonding. So always when such kind of situation arises, so you flood the top of the pile and then immediately do that testing. So what action to be taken when you find a defect near the pile? So there are many ways of handling the situation. So let me give you some case studies. So what we have done as a forensic studies, that were also one of the questions. Is there any chance to get a different results between CAT and PIT in the same pile? Perhaps yes. Your elevation of testing in PIT and CSL, it should be same. If not, it will be different. Your wave speed also, you need to calibrate between PIT and CSL. Your wave speed error will also shift your defects between both the methods. But if you are following the step-by-step procedures, probably will have defects identified in similar depth. The sample basis, I gave you 2 data sets having clear indication of defect by PIT and CSL at similar defects. All right, thank you for asking these questions. I hope I have answered it. So let me continue further on the thermal integrity profiles. So to overcome the limitation of the pile integrity test and the cross-hole sonic logging test, welcome Harun Pandit. So please hold on your questions. Then probably after I finish another 15-20 minutes, you can shoot your questions. We can have some more time to discuss. Okay. Okay, so thermal integrity profile is a newer method of evaluating the integrity of deep foundation element. Like CSL tubes, you have to embed the thermal wires. The yellow ones you are seeing is a thermal wires which is run all along the length of the reinforcement cage. Okay, and these thermal wires have thermal sensors. You could see this is the thermal sensors, and another 1 feet you have another sensor. So thermal sensors are there at every 30 centimeters, 1 feet. So you need to have these thermal wires as much as your CSL tubes. For every 300 millimeter diameter, you have 1 thermal wires, like we have 1 CSL tube for every 300 millimeter diameter. For example, 1.4 meter diameter, 1.2 meter diameter pile, you have 4 wires embedded along the reinforcement cage. But if you are trying to scan a diaphragm wall panel, so you need to have the opposite wires on the symmetry. The maximum linear length of these wires on one side should be around somewhere between 800 to 900 millimeter, not more. And you should have wires opposite to have the alignment of the cage evaluated. Okay. So as you pour the concrete, the hydration process generates heats. So these temperatures measured during the hydration process help to evaluate the integrity of the pile. So the temperature during curing is directly related to concrete quality, volume, and the radius. The reduction in temperature indicates necking or inclusions of poor quality concrete. while the increase in temperature indicates a bulge or increase in the impedance or increased concrete cover. Variance in temperature between diametrically opposite wires indicates cage alignment or cover issues. Okay. And so acquiring volume data allows temperature to be converted to radius. This is very important information that we need to have. Perhaps you need this even for your PIT or even your high-strength dynamic test, particularly for the drill shafts, to the accurate volume. So you can actually model your impedance profile versus depth, pile depth. So we use this volume for your radius conversion in this thermal integrity profile. So this method evaluates concrete both inside and outside the cage to assess both the cover and the alignment. Okay. Now, and you are testing 100% of the cross sections. Unlike your CSL, you are only testing within the reinforcement. This method evaluates shaft during the curing process as early as 12 hours, depending on the mix design and the pile diameter, and allows constructions to progress much faster. Significant cost savings can be achieved if we can save many days or weeks on a project. Okay, I'll explain to you a couple of case studies and how this thermal integrity profile has really helped to improve the schedule and to detect the problems very early in the stage of the project. ASTM 7949, I just found out recently that this has been withdrawn. Perhaps maybe it is under revision. So I'll try to find out more. Maybe I'll give the information as and when I get it. Now, during the hydration process, the maximum temperature will be at the center of the core. And if you are making measurements on opposite sides along the reinforcement cage, the temperature at the reinforcement behaves linearly with radius. Now, if you have a cage, okay, and you have wires and two sensors, one is the green and the purple, and this reinforcement is tilted to the right side. If this is tilted to the right side, that means the purple is towards the soil and the green is towards the core. And therefore, the green measures a higher temperature and the opposite wires measures a cooler temperature. Okay. When you see the opposite wires having a warm and a cool temperature, this indicates your alignment issue of the cage. Okay. Because the dispersion of the temperature is from center to radially outwards along the shaft, except one diameter towards the top and one diameter towards the bottom. Okay. And now you see the shift or a tilt in the alignment issue also gives you the opposite wires having cooler and warmer temperatures, while the black one is an average. If there is no alignment issue on the cage or the cover issues, I think all of these wires, the temperature measurement should have collapsed and you should get an average black one alone. One minute. Yeah. So, except the top one diameters when you have a roll off, because the dispersion of temperature is not only radial, but also it is towards the ambient temperature to the air, and the bottom it is towards the soil. So I'll explain to you how to address this. But here, unlike the previous slide, you only see a defect or a reduced impedance or inclusions at some depth. So the purple one, the measurement shows a cooler temperature, while the opposite one do not have any change in temperature. It matches exactly the average temperature. So this clearly indicate to us there is a defect in this pile or a necking in the pile. Okay. So when you see a low cooler temperature, and corroborate with the crosshole test, the complete loss of signal in the waterfall diagram, which corroborates very well the coring data also shows there is a severe defect in the top of the pipe. But if you do a PIT test here, or the PIT test will look like, somebody asked me the question. So the PIT will always look at a larger pulse width. But if you do this testing with a small hammer, then you get a sharp peak, lesser pulse width, and the positive signature just close to the pipe top. So if you use a bigger hammer, this larger pulse will mask your defect close to the pipe top. That's where your calibration of your hammers becomes extremely important. Okay. All right. Sorry. Let me go to the slides. Just wait for a minute. Yeah. Okay. So the volume of concrete is extremely important. So we will have this average temperature related to the average radius like this. The accurate volume information is critical to the analysis, requires thermal field log on concrete logs. The average radius is based on volume input over the given length. You have our average, the temperature average. We already seen that from the wires that we select. And there is a temperature to radius multiplier. So this will help to arrive at the radius versus depth. Now in the top one diameter and the bottom one diameter, you have the roll off. So we need to make that adjustments to determine the bottom of the shaft. And this is geometrically a hyperbola. And from the average temperatures on the shaft, you need to arrive at this transition point or the inflection point from the energy producer to energy dissipator. So this inflection point will be your bottom of the shaft, but it shall not be less than your actually shaft length. Okay, so that corrections to the bottom of the shaft could be done by this hyperbola. And same with the top of the shaft, you have the average temperature on the shaft. And this roll off is actually to this temperature, the top, the ambient temperature will actually over predicts the radius, and therefore it is to this top element. Okay, and this roll off adjustments could be made in order to evaluate the quality of the shaft. Suppose if there is a toe defect, then you do not see this kind of roll off, but some other shape. Okay. Now, as you pour the concrete, after placement, you do not have any measurements. As you continue pouring the concrete, the bottom portion start hydrating first. Then after half the peak temperatures, you already see the average temperature, except the top one diameter and the bottom one diameter is exactly a good roll off happening. And therefore, most of the analysis is performed at half peak temperature to one peak temperature, that is during the hydration process. Okay. Now, if there is any defect in the shaft, you will also know very early during the concrete placement. After 10 hours, you see there is a defect. 20 hours, the defects is already visible. So you have the average temperature, and 40 hours, the magnitude of defect is getting diminished. If you try looking at 80 hours, maybe it will vanish. And therefore, your integrity evaluation should be during the hydration process, somewhere between half peak temperature to one peak temperatures. And this one of the limitations of PIT, this thermal integrity, that your testing is during the hydration process. So if you pass that hydration process, probably you will not get any meaningful results. Okay, so as you pour it after 1 hour, this lower and warmer temperature on the opposite side of the wire indicates your cage issues, the cover issues, and it is getting hydrated. You get an average temperature. Probably you get a higher, warmer temperature towards the top is because there's a casing. So that prevents dispersion of the temperature towards the soil, and that's where you see a warmer temperature. towards the top, but the average is very good, except the alignment of the cage. There is no serious defect in the shaft. Okay. Now this is at 2 hours. Okay. 8 hours and 18 hours. So what do you make out of this data? Set at 8 to 18 hours. Please type out in the chat box at what location do you see any defect? Is there any issue in the cage alignment? Please type out in the chat box only. Please type out in the chat box. Do you see any defect in the pile? Yes, around 37.5 meters. So all the wires shows a cooler temperature indicates a defect. And you see in alignment of the cages, where you see the wires, the opposite wires has cooler and warmer temperature. Okay, and this is a splice location that is marked here. Yes, Bharat, Jamil, fantastic guys. I think some of you already have the experience. So you make early measurements, already reveal defects. Okay, and this defect is very, very clear. So what do you require the testing equipment? So you need the wire and which comes with the thermal sensors embedded at every 1 feet. Okay, and this wire has to be collected for data using the thermal acquisition port or a thermal aggregator. I'll explain to you what is this TAPN, TAG mean, and you need the tip main unit, okay, to download the data from the tab boxes. So each of these wires should be connected with the thermal acquisition port or a tap. Okay, so it starts collecting the data the moment you plug it with a user defined time intervals. Usually it's around 15 minutes. The temperature measurements are recorded. And later on, once you pass your peak temperature, or maybe the following day, you can plug in your thermal integrity profile main unit and download the data, or you can send the data towards the cloud. So the tag is a thermal aggregator. If this also acts as a tap on one of the wires, and this tag will aggregate the data from the remaining tabs in the pile or around the pile, and then send the data to the cloud. Okay. So you also need a thermal wire tester to ensure that the wires are functional. So when do you test it? You can test it when you unroll the cables before you rig up to the cables to the reinforcement bar. And after you rig up, you test again. Once the cage is lifted and lowered into the concrete, you test again before pouring the concrete. And just before pouring the concrete, you are sure your wires are functional. If there is any problem in any of those nodes, you can always note on, and later on in the data processing, you can actually turn off those nodes. So the PDI manufactures the wire with this 5-digit serial number for each of those wires, and you have different nodes for these thermal sensors. Okay. You have the tap and the tag, several taps and several tags, and the tag will send the data to the cloud. Now, if the piles are less than 30 feet, you do not need multiple tags, and one tag is good enough to aggregate the data and send it to the cloud. You don't use a tag, it's fine. You can get into a main unit and download the data. So if it's more than 30 feet, you need multiple tags. Well, okay. Now the instrumented cables are attached the reinforcement cage prior to the concrete, and you see the wires running along the reinforcement cage, the thermal sensors at every 1 feet. Okay, and for every wire you have the tap, the thermal acquisition port. Probably one of them will be the tag, the aggregator. So how to accept the data? This is again a very important. The load carrying requirement be controlled by the perimeter along the side shear or the skin friction, and you're interested in the compression is an axial loading, or if it is for the lateral loading, it is a structural bending. So these are directly related to circumference, particularly the shaft resistance. If it is an end bearing, it is a cross-sectional area. The lateral is the moment of inertia. So circumference is linear with radius. Okay, area is square to radius and moment of inertia is both power. And therefore, if you evaluate a reduction in the effective radius by this temperature measurement, for example, 10% reduction in the effective radius, you will reduce your skin friction by 10%. You reduce your axial loading with the bearing towards the cross section by 20% and your structural bending by 35%. Okay, so therefore it's very important that we accurately evaluate this. So in the PIT and CSL, probably we approximate in PIT, but you can have more reliable estimate of the cross-sectional area along the length of the shaft. So the recommended tip criteria is satisfactory if you have a 6% or less reduction and the cover criteria is met. If it is more, you may have to evaluate further for a reduction of the effective radius more than 6%. And usually the cover is given by some guidelines. So if the tilt is anticipated, probably even after tilting, you may have to have a minimum cover and therefore the net cover is sufficient. So you allow a little larger cover for allowing the cage eccentricity if your construction process actually predicts that you may encounter some eccentricity. So let us look at some field examples. So 350 drill shafts were planned to be installed in a project. The length of 39 to 56 feet. Temporary casing was installed. Groundwater at 44 feet below the pile top. Okay, and all these shafts were tested with tip. Now, as you could see that the temperature measurements, the average measurements, which gives you a reduced temperature reduction and thus a reduced effective radius. All the 6 shafts that was tested initially had this defect close to the pile top. Okay, all of them close to the pile top. So it really puzzled the contractor. They went to the drawing board to do the root cause. Okay, and the coring details also revealed that there is some concern on the concrete towards the top of the shaft. So here is the layout. First 6 piles were tested. If you were to do the testing with tip and CSL, by the time you get the data, 40% of the pile would have already been cast. But right now is only about 6 piles are being cast. And then they went to the to analyze the root cause. They found that the pulling the casing, the soil below the water table is collapsing faster because they're pulling the casing faster. And they changed the construction process, and only the 6 piles has to be remediated. That the balance piles were actually of good homogeneous because they already corrected. Okay, just imagine if you do not have, so 40% of pile has to be remediated. Okay, so all the 100% tips testing was made on the shaft and identified the 6 shaft with defect because of the groundwater approximately 4 feet below the shaft is washing out when they are pulling the casing. So they made some changes to the construction process and they mitigated the problem. Okay, and the construction techniques were modified to avoid further issues, and early detection saved considerable cost and delays for the project. Now, in another example, it's a wet shaft. This was data supplied by US PDI. 118-inch diameter, 10 tip wires were installed. Okay, let us look at the data sets. So it clearly indicates a cooler temperature. Okay, and of course the alignment of the cage also is an issue here. Okay, 7 and 8, wire number 7 and 8 were also showing a very low temperature. Okay, 7, 8, and 9 slightly. Okay, now, and they started to target those regions to core it. The client said they wanted to core it at multiple locations. So 7, 8, 9, and these were the cores that were of interest because that was revealed by the tip testing. And they actually cored this, and you see a loose material which corroborates very well with the tip testing, and this was later hydroblasted and pressure grouting was performed. So one of the remedial measures is to target those defective zones and grout it. Okay. The shaft shows a local reduction near Ys 6 through 9. Okay, and then they were able to find the defect. The reduction local radius is 32%. Okay, and the coring was done in several locations, but those 7 and 8 was critical. They hydroblasted and remediated. So this is a tip, a PIT result. So what do you make out of this data set? So please type out on the chat box for me. What do you make out of these data? Please type out for me. What do you make of this PIT result? Hello, everybody. Can you please type out what do you make out of this data set? It's a bulge in the pile. Probably it may not be a bulge. It's a damage around 15 feet. Around damage is around 15 feet. Defect in the pile, defect in the pile, making in the pile. Fantastic, guys. You have actually caught this data set. So you see a positive response in the velocity profile, very close to the pile top. So there's a necking in the pile top. Yes, necking in the pile top. So when actually you do a tip testing as well, and you see a localized cooler zones close to that same level as close to the pile top around 15 feet. This is same as indicated by your tip and the PIT as well. So both PIT and tip identify major defects. Thank you. Fantastic, guys. Okay. So, what is the limitations of this tip testing? The tip testing, you require the wires to be embedded before pouring the concrete like your CSL. You have to do that testing during the hydration process. If you forget to plug in your data loggers, you will not have any data sets. Okay. And you have a lot of advantages as you can get the status of the shaft very quickly, very early during the construction process. So let me share with you some 2-3 case studies before I conclude in about 10 minutes time. So recently I was on a project which actually installed around maybe 1,500, 2,000 piles, cohesion-less soil into the weathered rocks. There was a basement for the project. It's a high-rise building. The top 6 meters were actually a dummy pile. Okay. Now these piles were actually installed without any casing or a liner. You know, cohesion-less soil is very difficult to hold the borehole clean. And they installed the piles, all of them. So when they started excavating to the basement, slowly after 3 meters, 4 meters, they could see some top of the piles. They're a little puzzled and surprised now because their elevation of the top of pile is minus 6 meters, but at 3 meters, they could see that the concrete is overgrown. Then they finally saw that the concrete has overgrown when they do the testing, multiple PIT tests. And you see the bottom 3 meters probably is very defective. There's a collapse of the borehole, and therefore you see the pile is going up. So the volume they know, and they realize this only when they started excavating to the basement after installing all the 2,000 piles. So what if you would have done this thermal integrity profile in the same project? The first few piles, you would have already known there is a severe problem in the drill shafts. They could go to the drawing board, root cause that issue, probably change the procedures. They would have mitigated, right? Now the piling is done. You spent around $8-9 million. Now the remedial measures to counteract or do some other changes in the foundation systems going to cost them another $4-5 million. So it's literally waste of time, waste of money. Sustainability is a question. So the tip testing could be one of the answers to eliminate such kind of problems. And this is not one project that I'm talking. I can quote you maybe some 2-3 projects that I have recently been involved that has this kind of issues. So there's another project people tend to have this data set from PIT. This is an European equipment which actually interprets as a mirror image of whatever the data sets that we have seen right now from the American system. Okay, and this shaft is reported to have been good as far as pile integrity is concerned. But there was some suspicion on these data sets, so the client wanted to retest all of the piles. When you actually retest, you could actually see, maybe I'll ask you, what do you make out of this data set at the bottom graph? Can you please type out in the chat box? Please type out in the chat box. What do you make out of the bottom graph? No skin friction. So this is a PIT test, Gautam. So skin friction, you cannot make it. So it is damaged towards 32 meters. Yes, you are seeing a positive response around 32 meters. Around 32 meters, and therefore it is likely that you have some kind of impedance reduction at 32 meters, which is not actually revealed by the other testers. Okay, the around 31, 32 meters, fine. So the other set also, it was reported to be having good pile integrity, but even that mirror image response, if we carefully look at, you see a negative response before the toe, and you see a positive response before the toe in the American system. Is this a reduction in the impedance or impedance change around blood depth? Probably it's masked. So is it because the people doing this are not aware how to interpret the data, are not aware what to make out of the data set, or is it an intentionally to mask the data sets? We are not aware of this. Okay, could be anything for that matter. So we're not being judgmental here. So all the point I'm making is there is possible error in the interpretation of the data, and also you are compelled to do this if you do not have good data. So let me show you some more data sets. Okay, so this is a CSL scan in the major diagonal. All of you are very familiar now. There's a complete loss of signal toward the toe, but there was no mention of any of these defects in the CSL test by the other agencies. Okay, where the retesting clearly shows that there is a major defect. And so with the perimeter, all the perimeter of retesting shows defect, but all the perimeter data set from the first time testing revealed that the pile is having good shaft. Again, so is it because there is some error in the data set, or people are not aware to interpret the results, or otherwise? So the question is the same. Okay. Another project recently, it was a residential building, about 5-6 floors building. There are a lot of monopiles being installed around the pile, and series of touch piles to retain the basement excavations, which ultimately during excavation it collapsed due to rain, and also these piles were all cast single pile monopiles. Some of the piles were tested, integrity was fine in some of the piles, and one of the pile, maybe this or this, were tested for high strength dynamic test. Let me show the results in a bit. When you look at the geotechnical data, okay, the refusal to N values is reported to be around 7 to 8 meters. And that is where they terminated the pile. So into the rock where N equal to 100. So termination criteria is very suspicious. Okay, I do not know how to evaluate the termination criteria. Say N equal to 100, they stop here. So when I actually did the pile failed. So let me show you the result of the pile. The reinvestigation, the DCPT, the dynamic cone penetration tests were performed. The excavated basement level, those levels, and then you see the refusal stratum goes beyond 14 meters, while initially below the ground it was evaluated to be around 8 meters. There is no refusal at the 8 meters. Now all the piles were terminated at this zone because the geotechnical data revealed that refusal stratum is at shallow depth. Okay, and you do the PDA test, displacement of the pile 19 millimeters. Although this is error, fine, no problem, but still the pile is moving. The refusal stratum, the pile cannot move because the pile load carrying capacity is around 170 metric tons. And also you see the integrity factor of 59% is broken pile. There's severe damage. You need to have 100% for an intact pile. Probably somewhere more than 85% is fine because there is some reduction in the impedance, but 60% or less is a serious defect in the pile. When you do the PIT on the top, it also shows serious defects towards the pile top, which very well matches with the PDA test. Okay. And the pile is moving, so it can't take the load. So when you make a reassessment of capacity, where the piles are currently embedded is only taking around 70 metric tons as against 170 metric tons. So it's almost 3 times higher capacity. They have designed the pile, so it's only taking about 1/3 of the piles. Okay. So what do you do in such cases when the pile is already ready to put pile cap? Some of them were already capped, but testing was not performed on all the piles, and some testing revealed the defect in the pile and also a very less load carrying capacity of the pile. So we have to remediate this for further. So when you are taking the data set from a very bad pile top, which it is in this case, okay, an unguided drop on the top of pile, okay, and you mount your very sensitive axiometers without preparing the surface of the pile set, so you tend to have very shabby data. So this is also a forensic study with all the 7 piles tested by PDA reported to have achieved a capacity about 415 metric tons. When you re-looked into the data set, the force velocity time history, now here is the capacity issue, both force and velocity exactly on top of each other. There is no separation. That means the capacity is 0. But still, the capacity is reported to have achieved 420 metric tons of total capacity. So the software will not do this mischief. So there could be several reasons. People are not aware how to collect the data, how to assess the quality of the data, how to interpret the data. So if you do not have a good data set, the contractors put lot of pressure under duress. You tend to give some reports to satisfy him. So whatever the reasons, what the point I'm making is simple. So we need to learn how to do the test right in the first place, and therefore training is very, very important. And I can show hundreds and hundreds of files, data sets, which we get it for second review almost every day. Okay, here is another set, force and velocity not at all proportional. Okay, no, force, velocity, proportionality is 2.2. It should be unity, but still with this shabby data, people tend to further analyze in the CAPAP software and try to present the results of achieving 350 metric tons of capacity. And you see the impedance profile is so shabby, you cannot have the cross section of the pile like this, right? So it's not the problem with the pile, probably it is problem with the analysis, and you could only do this analysis because the quality of data is very, very difficult. And in the CAPAP, you cannot have a match quality more than 5. Even though the software objects that you have a quality of 5 or above, that it is really not good, you tend to overrule the CAPAP software and tend to output and present the results. So perhaps you may not have good data set to analyze, not that you may not know how to do it. So therefore, it is very important that we actually collect good data sets regardless of the test procedures, PIT, PDA, even the cross-hole sonic logging test, thermal integrity profiler, or any other test, even your static load test. So we need to know how to do the test, theoretical background behind the test, and how to assess the quality of the data, how to interpret the data sets and the results, and the application of the data sets. So there is a proficiency test PDA Pile Dynamics conducts this proficiency test. You can go to pdaproficiencytest.com and you can see the people around the world who has attended this test and this course. I'm very proud to inform all of you that around more than 20 of our engineers are certified advanced level or higher in this heightened dynamic test, PDA proficiency test. This gives every one of us an immense confidence that whatever the basic minimum requirement is there, we tend to fulfill that. So people know how to do the test, how to assess the minimum standard of data sets and the interpretation of results. And therefore, I encourage all of you to get the trainings, attend this, regardless whether you are a tester, you are a quality engineer, you are owner's representative, you need to know integrations of all these methods, and these certifications will give immense confidence to all the stakeholders involved in the project. So with this, I conclude these presentations. I'll be happy maybe another few minutes to take any of your questions. Please put it on the chat box so we can discuss that. And further, I will ask Sangeetha to take over now. Sangeetha, are you there? Over to you, ma. Let me see if there is any question in the chat box.
Yeah, sir, I'm here.
Yeah.
You can, if you have any questions, you can just Mr. Chat box. Yes.
So in what percentage of files are TIP usually done? So that's very, very subjective. Some of the projects, they are doing TIP on 100% of the file. And if some of the projects which want to assess the construction process, they are usually doing it on few initial files. They already know that construction process have problem or no problem. You already seen two case studies. I just showed you one on the TIP data and one without any data set, which actually have a lot of problems. If they had done the TIP, they could have eliminated the project. And this TIP has to be tested during the hydration process. So usually the one peak diameter for a circular pile, it could be somewhere between 24 hours to 48 hours. You'll be able to get the peak temperature and the data sets. If you are measuring temperatures to a diaphragm wall, for example, the time could actually extend up to maybe 40 to 60 hours or even more to get that peak temperature. I hope I have answered all the questions. What strain measurement in instrumented load cells, strain force, concrete in the instrumented load cells will get you the load transfer along the length of the shaft. So that may you can correlate with your geotechnical data set or the load settlement curve itself. So, okay, so can all of you come on video so we can have one pic before I hand over to Sangeetha. Please come on video, please, all of you. You can turn on your video, please. You can turn on your video. What are the punch points that we need to check for acquiring good data from dynamic load test? So the first thing is your pile top preparation. So you need to remove all the contaminated concrete and reach to the sound concrete. Okay. So from there, you extend the reinforcement bar with the formwork, you pour the concrete, get the top of the pile to have good leveling. And once you have a sound test section, then at any depth where you want to instrument the pile, you mark the locations where you want to drill the holes for the sensors. You need to have these sensors fitted along the axis of the pile. So those test sections should be nicely grinded, flat surface, smooth finish where you can grip the sensors to the pile. Particularly board piles, you use good quality, high strength anchor bolts. And for large diameter board piles, more than a meter diameter, we usually encourage and recommend to use 4 strain gauges and 2 axometers. Okay, because if you are usually using 2 strain gauges, one of them is bad, the other set you cannot use it because minimum strain gauge is 2 numbers to compensate for bending. Okay, so once you have this good instrumentation, you will get good quality data set. So you need to assess the proportionality. So if you have good proportionality, good tour response, the data set is of highest quality, your analysis interpretations becomes extremely easy. Okay. So embedded sensors into the pile using high strain dynamic test. No, we don't have any experience of embedded strain gauge during high strain dynamic test, although we use this embedded strain gauge for the SPT energy measurements during the geotechnical investigation, and those are embedded strain gauge. But normally for high strain dynamic test, we use a reusable strain transducers, not the embedded strain gauge. And this works in the same principles. So piles, we are not using it only for the SPT energy measurement. We use the embedded strain gauge. So before accessing to the CAPREPs, yeah, you need to assess the quality of the data. So you need to have the data set start from zero. You need to have good proportionality. You need to have this force and velocity returning to zero. Then look at your individual sensors, the velocity, individual velocities, are they exactly on top of each other? If not, you can turn off one of them. You look at your strain sensors, maybe you have bending, severe bending, opposite bending. So if you are able to look at these aspects and ensure that you have good quality data, and one of them you to look for is your wave up, upward traveling wave. If there is a gradual rise in your upward traveling wave without any step in, so your proportionality is assured, and also the displacement records to be integrating nicely to your measured final set. So don't go with, if you are a user, go with the DFN measurements from the PDA, but you actually physically measure for every blow what is the net displacement and use that net displacement before you bring the data to the CAPREP. If you're able to look at these few things and assure the good data sets, probably or even your CAPREP becomes extremely easy. So I sincerely encourage that you please try to improve your data acquisition methods and procedures, train the technicians who are skilled, and you can send them to us. We will definitely train, because it's our professional responsibility to promote good practice. Okay. And then you can collect the data. You can have a shabby data, you can have a good data and analyze yourself, and you know how easy it is if you have a good data vis-a-vis extremely difficult if you have a bad data. Thank you for that. So Sangeetha, over to you.
Yeah, thank you. Thank you very much, sir. And I hope all your questions are answered. So let me share my screen. I've shared you one feedback form in the chat box. You can just comment your thoughts and other feedbacks, or if you have any other questions to address, we will address that in our upcoming session. So as you can see, and also Dr. Parthasarathy already mentioned, as Sarathy Geotechnical is concerned in our forensic department, we are receiving a lot of projects in which initially the client is like not doing proper practice at the site and messing up the entire project, and as well as the foundation design is concerned, which is turning to lot of time as well as cost issues. So as Sarathy Geotech is concerned, we are trying to educate people on good practices and how those mistakes are not repeated in our future project. And we are trying to bring some quality and some standardizing the practices to get good quality results. As you all know, the geotechnical data that we collect from the initial phase is having lot of importance as with respect to time as well as the cost of the project. So it's been a while that Sarathy Geotech is conducting offline events. So many requested us to conduct an offline event for quality assurance and quality control on deep foundation testing. So we are coming with an exclusive training program for 3 days, in which the good practices along with the case studies is also included. I will explain the modules in the coming slide. The venue will be Bangalore. And before going to the module, I just want to introduce TAQELL Edification Private Limited. which is an exclusive training partner of Sarathy Geotech and Engineering Services. And we are the technical partners of File Dynamics in USA as well. You can see we have some list of offline and online training programs, from site characterization to case studies to rock engineering, ground improvement, geophysical. So you can contact us for the future reference. So on this training in the month of June 23, 22, 23 and 24, we are starting with a good practices in geotechnical investigation. You can see entire module, entire program will be explained with a real time case studies, and you will get a hands-on experience about the PDA equipments as well. So geotechnical investigation, good practices. And before that, we'll always start our program with a pre-training assessment quiz in which you can see yourself at which stage you are standing at. This program, we are recommending for beginners, intermediates, as well as experts. You will get an overall idea about QnQC on deep foundation testing. So next comes the standard construction practices and challenges with case studies, which will be for 1 hour. Then we will list out some load test methods and how the data is interpreted, how the results are interpreted along with the case studies. First day, afternoon, we'll introduce about the deep foundation techniques, testing, as well as wave mechanics. So you'll get an idea of the basics of wave mechanics as well, which will be very useful to interpret the results. Going to day 2, we'll come in detail to file integrity methods, in which PIT, CSL, and as Dr. Parthasarathy referred, the new technology, thermal integrity profiling, will be introduced to you. And afternoon, we'll come to the proper practices and data interpretation, application, as well as quality assessment. Moving to the last day, we'll have a quality assessment before the pouring, that is shape and squid, which is very important to determine the bottom contamination as well as the profile of the file. Then we'll come to cap WAP theory and equipment demonstration. We'll get a real feel of like equipments, how it is used, and our experts will be explaining on that. In the afternoon session towards the closing, cap WAP data review and problem demonstration. You will get a chance to do yourself a problem using our cap WAP software. Then we'll have a post-assessment quiz, and later certificates will be distributed. So this is the overall module, and I can share, if you can share your feedback, I can collect your email ID and I can share you the further details of the program as well. So I request everyone to give your contact details so that I can share it with you via email as well. So usually we used to have a 2-day program. We are intentionally stretching into 3-day to have a better understanding, and you can get the maximum benefit of this event. So the event comes with a cost. Usually we used to charge around 25,000 for the event, but you are getting an early bird offer since you are attending our Q&A session of deep foundation testing. So people who make quick decision wins, and we encourage you to take this early bird offer. So what you can do is, I will just leave a link in our chat box. So you can book this event for 5,000 rupees, and within 48 hours, you can pay the remaining amount. So the venue will be TAQELL Edification Private Limited, Jayanagar, Bangalore. And I will share my contact number also is shared. You can contact me if you are facing any difficulties. And one more thing, as a service providing company, we also want to support a lot of students who are coming from a very low financial background. So we can waive off some this coaching fee for them. So they can contact to this number if you are a student who completed PG or graduate and who is jobless, and if you can provide some certificates that you are coming from a weak background, we can support you on giving you training. We are showing that social commitment as well. So I hope you got the link to do the payment. We'll give around 10 minutes. And if there is anything in between, you can post that in chat box. I will share the QR code also. If you are facing any challenges using the link, I will share you the QR code in the chat box as well. If there is anything, please let me know.
Yeah, while some of them are making decision to attend this program, so please type out what are the 5 key takeaways from this session as well. When you are making the decision to attend or not attend, please type out what are the 5 key takeaways from these sessions. Please put it in chat box. Yeah, all of you, please.
June 22, 23, 24 will be the dates for the offline training session. The venue will be in Bangalore. Once you can fill out the feedback form, we will share you the location and further details, and you can follow our LinkedIn page as well to get more updates. And we will be soon starting our TAQELL page as well to get you more updated regarding our upcoming training program. Yeah, Partha sir, if you would, as Partha sir mentioned, you can also mention the 5 key takeaways from the session. So we are putting a 10 minutes timer. After that, we'll officially close the event. So you can take the decision. Those who make the right decision wins. So it's a very good early bird offer exclusively for people who are present in our Q&A session. So we already shared the QR code also, the link also. Yeah. Yeah, thank you everyone. So almost 30 seconds remaining. So I just want to tell you that if you have any concerns or queries, please write a mail to me or you can directly contact to me. I've shared my details in chat box. So thank you very much for your participation. Please reach out to us in case of any queries or any other concerns. Thank you everyone. Thank you.